Hey guys, this is a teardown of a Vision Research Phantom V5 high-speed camera. This was provided on loan for teardown by Nathan from Aimed Research, which is a high-speed camera rental company. He saw my previous video on the Phantom V4 and thought it would be nice to see what the next camera up in the line is like. These two are quite different in size, way bigger. This one is 1024 by 1024 resolution at 1000 frames a second, and this is 512 by 512 at 1000. Apparently there is a problem with this camera. From what I understand, some of the vertical columns on the image sensor are dead or could potentially be caused by bad ADC channels, but we'll hopefully find that out during the teardown. First of all, let's give it a try powering it up just to make sure, so we know what state it is in before we tear it down, so we can compare that with what it's like after. The main capture connector, as they call it on these cameras, is identical, although they've brought out a separate 24 volt power input on the V5. So I'll hook these up. And for those of you who don't know, I just started up an account on Patreon. Getting teardown gear like this always costs money. I had to buy this camera off eBay. This one I have to pay to ship back to Nathan after I'm done. So any contribution is greatly appreciated. If you contribute at least $5 a month, I'll put your name in the end credits of all of my new videos. Okay, here we go. And nothing, zero current draw. So it turns out that the connector pin numbering on the datasheet is a mirror image for this connector while it's not for that one. Kind of a trap there, but I've got that fixed. Luckily this has reverse polarity protection diodes and everything, and fuses, so there's no real worries of hooking it up backwards. So let's give this another try. Powering up, drawing 0.73 amps. No video yet, although we are getting 24 volt light and firewire light. And oh, it would help if I actually plugged in the video. There we go. Oh, we're getting some weirdness there. The display is going kind of crazy. We have one quadrant out of 4 working. Yeah, let's put a lens on this and see what we get. This is just a Nikon F mount. I'm actually going to have to wedge the iris open because this doesn't have any manual control, so you have to wedge that open. Okay, yeah, we're definitely getting something of an image there. Yep, we're definitely getting somewhat of an image on that top right, but everything else is just completely dead. Actually, no, it's not. If I shine a bright light into it, that's odd. Each quadrant has a different problem. This one is just too dark. This one has some sort of weird, I don't know what you would call it, data going to the wrong position. This one is just completely garbled. So we know what state it's in. Let's get to tearing this down. I just noticed that the bottom display not only is garbled, it's also mirrored, and looks like there's a few dead pixels near the bottom right, although that could just be an artifact of something else, but this is really weird. Let's just see if giving it a few whacks changes anything like it did on the other camera. Nope, that seems to be relatively stable. Like the V4, this has this rubber cover thing that doesn't seem to have much point. The construction is definitely different from the V4 because there's no there's nothing on the side for assembly. Come on, there we go. Yeah, it looks like the top is going to have to come off. And let's see, this is probably going to have a gasket, so let's see. Come on. Oh, I gotta get a screwdriver. No, it's not coming as freely as I would like. I just don't want to risk damaging anything if, for example, boards are attached to the top of this. Let's see. There's definitely something there, so I'm going to try removing the side first. I have an inkling someone's been in here before because these screws are of mismatched lengths. It looks like these ones on the side should be shorter, but someone has put, it looks like put some of those into the top. So it looks like the back actually comes off first. Typical, really nice machining there. And now what? The front is sort of loose, but not quite. How is this thing built? There we go. Oh, there we go. Yep, same thing. Oh, look at that. These, can't believe the quality that goes into these things. Okay, we're getting a little view inside here. Two sticks of RAM. I can just read, it says 128 megabytes on those. So this looks like there's 4 boards that have them. So that puts this camera at 1 gig, which is about 1 second of record time. Not a huge amount. I think this also had an option, just like the V4, for those extended sticks with 4 gigs of memory total. I just noticed this has a label saying US Naval Academy on the back. Also confirming the 1 gig memory option. So it looks like Vision Research labels these cameras when they were built as to who they were sold to. That's interesting, because the other camera, the V4, said it came from Sandia National Laboratories. Okay, that's starting to come apart a bit more now. There we go. There's a better view of that board. And yes, so it does, oh, okay. So they've stuck it down to the top. That's why the top wasn't going anywhere. So it looks like we'll just have to carefully prise the bottom off with these sticky things. So yeah, it definitely has some compliance. Oh yeah, there it comes. I'm thinking these might be thermal pads. Oh yeah, those are cold. Those are most certainly thermal pads to get heat from the these board holders onto the sides, and also it'll of course go through here. Actually, I better get the front off because that's sort of flapping around in the breeze now. Let's see. That's easy enough. At least that card was easy enough. I'm probably going to take them off the sensor board. Those must be the 4 analog channel connections. Yep. Oh, this looks like a somewhat denser board than the other boards we saw in the other camera and elsewhere in here. There's just so much stuff going on in this. Stack of 2 boards. Bottom board has the image sensor, and there's a few board-to-board connectors taking the analog signals through. It looks like someone's been in here before, because these cards seem to have been put in the wrong order. Someone's labeled them, but these 2 sets, the analog acquisition cards, have been put in the wrong order. I wonder if that is what caused that weird reversal in the image we saw. Anyway, it looks like these just have 4 very long screws going all the way through. I'm thinking they go through all the way through. These screws look actually quite specialized. This doesn't look like any sort of a standard screw you would just find in a catalog, at least not any normal one. I'm wondering if they actually had these screws custom made. It's kind of an odd head. They've it's not really that even, like the machining on the tip, and they've ground a slot into it for slotted drivers. Yeah, these are really odd screws. Now, yeah, board-to-board connectors on one side. A few of these are already loose. There's some sort of like an oily or sticky thing holding them together. Okay, that's pretty easy. And let's get the rest of these cards out. The top edge of these cards that was connected to the heatsink with the thermal pad is all covered in this greasy stuff from that sort of seeps out of the thermal pad. It sort of gets on everything, and these are picking up dust pretty badly. I'm going to have to wipe them all off. There's 4 of these boards in the system labeled Phantom V5 memory board. These are designed in 2000, revision A, so they haven't, doesn't seem they've actually done revisions on these. There's a few little bodges with some tiny capacitors up here. This basically takes the 16 analog channels coming in from this connector from the image sensor board into 16 ADCs. These are AD9203. Those are 10-bit 40 megasample per second analog to digital converters. We also, of course, have the 2 memory modules, 128 megs each, rated 66 megahertz. And on the bottom we have some 74 16 646. Those are 16-bit tri-statable bus buffers and registers. And on the other side of the board, we have the other 8 analog to digital converters, and these are Cypress CY7C4205 18-bit by 256 FIFOs. Those buffer the data coming off the RAM or coming off the ADCs until it's ready to be written into RAM. There's more of those bus transceivers. There's the RAM on this, each one has a 64-bit bus, so we have to have 128 bits worth of bus transceivers, so the data in RAM can be read out. And there's a little small Xilinx FPGA here that's just used to generate timing signals, control access to RAM, control RAM refresh, control how the data is steered from the FIFOs into the RAM, and then from the RAM and read out on to the rest of the system for display. One little bodge here with a wire, though that just seems to be to do this other bodge they've done with those little tiny capacitors across the inputs to the ADCs. This looks to have differential inputs coming off the image sensor board because there's 2 connections going to every ADC. There doesn't seem to be anything under the RAM. I know this camera had an option to have longer memory modules. There are some very uncommon and very expensive back in the day SODIMMs that had that basically had 16 chips instead of the 8 that these have on them. They extended out to about here. And on the Phantom V4 teardown video, someone replied in the comments and said those modules cost about $500 back in the day each. I know this camera did have a 4 gig memory option with those. This one just has the 1 gig total. There's also some power supply filtering on the bottom of the board here. That's probably to feed the clean supplies to the analog to digital converters to avoid getting noise. All these boards have these stickers that say April 2003 on them with the serial number, and there's a little -1 or dash number written after each one, so I'm guessing that's the board ID. But it's odd, there's 0, 1, 1, and 3. I would have expected 0, 1, 2, and 3, so I wonder if one of these boards has been replaced or have been mislabeled. I just noticed that one of these RAM cards, the one that says -3 on it, does not have glue on the holding the RAM sticks in. All the other ones had hot melt glue holding them in, so someone has removed that. So now we can at least get in here and see how this is wired up. Yeah, nothing really at all interesting in there. This one, coincidentally, is bottom left, which had was one of the worst sections of the image that we saw. This is the PH5TB. I think that means Phantom 5 timing board, judging by the similar board that was seen in the Phantom V4 we tore down before. This has a huge Xilinx FPGA on it, an XC4020. That's in a 240-pin QFP package. It's a 20,000 gate equivalent, has about 700 logic blocks, 2,000 registers, It's a reasonably big FPGA. It's one of the higher ones in the range. That likely does timing control for the image sensor, but given this is the timing board. This also has a Hitachi HD 64F 7045. That's a 32-bit CPU running at up to 28 megahertz. That's connected to a 32 meg by 8 flash and a 16-bit by 256 SRAM. And there's another one of those on the other side. So this has a total of 1 megabyte of SRAM. And there's a small Xilinx CPLD probably doing glue logic. The connector on this side runs off to the image sensor board that goes onto this one that likely provides all of the timing signals. This connector goes off to the back panel board, and that just has I/O, various I/O like timing signals and trigger connections, etc. The board is quite dusty, but except it's been rubbed off a few places. I don't think I did that. That's someone clearly has been in here and has attempted to fix this probably. Elsewhere on this board we have some. These are some I believe opto-isolators for the isolated input. A lot of the inputs are isolated from the rest of the circuitry. This is probably a reset switch. There's a polyfuse for power supply protection. There's a RS-232 transceiver, max 232. I know this had a RS-232 control option. And not too much else. It's a 40 megahertz clock. I believe that's the RAM clock. We'll probably check that later when we power it up and look at it. There's a battery for the RTC. Not too much else on this side. And on the back there's just that other SRAM and a whole bunch of more bus tri-state buffers used to connect up to the bus that goes across all of these boards. And again, this has the same April 2003 sticker on it, which is a bit odd because a lot of the parts on this, like the real-time clock, has a date code of 99. The Max 232 has a date code of 2000, so either they made a whole bunch of these boards and they sat around, or this was an indication of when it was last serviced. I would definitely say this is the timing board because there's signals going from this connector to the image sensor board through some vias here. You can just see the traces under the board, and then over to the FPGA, which would generate the timing signals. And while moving these RAM cards around, I just noticed they have quadrants written on them up here. This one says bottom left, top right, top left, bottom right. So that's clearly where what the quadrant of the image these cards work with or store. Wonder if that must have been they must have written that while they were debugging it. On the Phantom 5 IB, I think that means interface board. We have another Xilinx FPGA, the same XC4020 as the other board. This seems to connect onto the bus that goes up to the acquisition cards. This has 3 of these 512 by 18 SRAM, so that's about 1 megabyte each. I think they're using these as image or fixed pattern noise correction buffers. We also have an Analog Devices NTSC PAL video encoder. That's connected to this small IDT FIFO 8K by 8 bits. That's probably to buffer data going into it that can hold about 2 or 3 NTSC lines, depending how they're encoding the video. There's also another small 1K by 8, or actually these are both 1K by 9 bit. I don't know if they're using the 9, they're probably just using the 8 bits, but yeah, 1K by 9, that connects up to the, on the other side of the board. There's another third RAM chip. And there's a Philips, what is that? PDI 1394, that's a IEEE 1394 Firewire link layer controller, and that connects over to a TI Firewire PHY, and those connections from that go over to I think that's chip supports 3 ports. This one goes out to the back panel, and there was a unfitted option. I think this is just for a regular onboard Firewire connector. What I think they're using these RAM chips for 2 different things. One of them, since they're exactly the size required to store a full image worth of data, I'm thinking one of them is used to store the fixed pattern noise calibration values. CMOS cameras like this, the sensors have basically an offset on every pixel. It's just something intrinsic to the sensor. A black on the image will be some value above 0 coming off, but every pixel will be slightly different. So what they do is you cover the lens, take an image and store that into one of these RAM chips, and then those are used as offset values that are subtracted from every image as they're displayed. Yeah, so I think one of the chips is probably used for that. The other two, I'm thinking, are acting as a double buffer for when they read out the image from RAM to be displayed. Because there's 8 sticks of RAM that the image has to be read out from. As far as I can tell, there's one common bus running on these connectors, 64 bits wide, that goes to all of the 8 sticks. So they each have to be, the data has to be read out individually. It's likely that one complete line of the image is split up across the two sticks of RAM, where the pixels come out in an order like, I think it would be 8 pixels from this stick, the next 8 pixels will be from this stick, and RAM is rather slow to start and stop reading. It's the best to read it in bursts. So what I'm thinking they're doing is reading the data out in bursts, even though it's not in the right order, and then they're ordering it as they write it into the RAM. That would pretty much solve the problem of how to read the data out into RAM for display. And they likely have 2 chips so that basically while they're reading it into the RAM, you can't read that out at the same time to be displayed. So they're reading it into one chip while the other is being read out by the FPGA and sent onto the display or onto the firewire port or wherever the data is going. There's not a huge amount else on this board, just there's a clock of about 27 point something megahertz. That's probably for the NTSC encoder. There's another probably crystal for the firewire PHY, and yeah, just passives and a few an EMI filter for a firewire. And this board also has the same April 2003 sticker. One other thing I noticed, a little bodge here where they've stuck 2 inductors on top of each other. I guess they needed to half the value. Although those look sort of like common mode chokes. I don't know why you would want to reduce the value of a common mode choke, although in EMI it's very hard to predict what goes on. I'm really starting to hate this stuff. The oily residue that is coming out is just getting over everything. It's making everything slippery. It's hard to clean off. Ugh. The last board in the card cage is the power supply board. This seemed to have a big DC-DC converter on this side, a lot of power supply filtering, a little small one, and a small, probably a linear regulator mounted to the case for heat sinking. And I also noticed this board has a pretty bad bend in it, actually, if you looked right down the side there, and that isn't even properly clamped down. I'm wondering if that is causing a problem. It looks like they have stuck, let me get a bit more light in there. They have sort of stuck more of that thermal interface material to the bottom of the DC to DC brick, and that seems to be pushing the board up really hard and causing it to bend. That cannot be good. I'll have to see if I can thin that down a little bit. See if I can get this off to remove that. It looks like they haven't put any thermal paste on it. I guess there's enough thermal transfer. They just need a little bit more heat sinking than none. A little tiny plastic insulating washer on that. You don't see those much anymore. So I was wondering what these little countersunk holes for. Turns out they're for only on the bottom module to hold it on. There we go, I think. Yep, that's feeling soft. Oh, they're all moving around. Yep, got to put that back on the base. Not a huge amount on this board, just 3 big DC-DC converter modules. These are all made by Ericsson. This big one is 3.3 volt at about 13.5 amps, 45 watts total output. Quite oversized. The whole camera draws about 25 watts when it's running. And these smaller ones are macro DENs by Ericsson, 5 volt at 6 watt out. There's 2 of those. I guess they have split supplies for noise, or they're using it for higher power or something. On the other side, yeah, just another small DC to DC, and this is an LM 2991 negative LDO. Wondering where they're getting the negative supply. They must be either running these to get a negative supply, or this little one is doing it. That's probably for some bias voltage for the image sensor, or something to do with analog. On this side there's a couple of diodes. This has apparently supports a battery option, which is basically just 2 inputs diode ORed together, so either the power supply or the battery can power the camera. The spec sheets for the camera says 18 to 36 volt, which is exactly what these modules are rated, so that's where that must have come from. Nominal input when this was 24 volts. Looks like they had an option for a different brick, a smaller one, but they decided to fit the larger one. Also, there's a lot of tantalum caps. Wondering if any of those have failed. That could be causing the problem we're seeing. Although, with one of the quadrants working properly, I'm somehow not thinking that's the case. Made in Sweden. Yeah, no expense spared on this camera. The back panel board doesn't have all that much on it. It's really just breaking out these connectors into much more convenient connectors to go from board to board, rather than having to solder all these little wires in. It looks like they've used solder cup terminated connectors, but they just mounted them into PCBs. It's interesting, the back panel has a different date sticker than all the other ones. I'm wondering, yeah, this camera might have gone in for service and they replaced all the boards except for this. And on here there's one little bodge for EMI suppression, likely a whole bunch of little surface mount capacitors soldered on what I presume are, no, that's the FireWire connector, so that must be power and the power connection for FireWire. Yeah, I must have had an EMI problem there. And there's a little dip switch there. I wonder what that's for. Now let's get into some of the juicy bits. This is the Phantom V5 driver board, I think. This breaks out all of the 64 analog channels to 4 connectors, and has another input for the timing signals and power. This has numerous drivers on it. Intersil EL7154, they call them pin drivers. These are 4 amp high power FET buffers. Those are to drive signals like clocks on the image sensor. There's some around this side of the board, and there's a few on this side as well. There's also a lot of Max 603 adjustable LDOs, and there's not too much else. There's a lot of passive filter capacitors. There's a LTC, what was it? LTC 1665 8-channel DAC. Hello, kitty. Yeah, 8-channel DAC. I think that's 8 or 10 bits, depending on the version. And there's just a bit of 7400 series logic. There's also quite a few test points all over the place. They must have to adjust analog levels on this while setting up this board. We also see more of these dual stacked inductors, or common mode chokes, just like we saw on the other board. So this just connects to the board underneath with some board-to-board connectors. So this should, it looks like there's 3 of them, so it'll be a little bit difficult to get this out. No, maybe not. There we come on. There we go. Ooh, look at that huge image sensor on this thing. Yeah, a big socket, and then in a PGA ceramic package. So it looks like there's not at all much in this board. This just breaks out the analog outputs onto these connectors to go off to the other board. Bunch of filtering. There's some more. What are these? These are just LMC 6482 dual rail-to-rail op-amps. Also of note on this board, there is another one of those octal DACs. And there's this chip, which is a little bit of an odd one. This is an LM84 diode temperature sensor. This is basically a device designed to sense the temperature of an IC junction by connecting it up to a diode inside the package, and it measures the voltage, forward voltage of that diode, which corresponds to the temperature of the junction, because the diode forward voltage drop decreases very slightly as the temperature increases. So this senses the internal temperature of itself and of the target device. This apparently, the datasheet mentions measuring the temperature of a Pentium 2 processor, I think it was. So they must have a diode junction inside this image sensor to measure the temperature, probably used to compensate for variations of the image offset with temperature, image pixel offset with temperature. On the other side of the driver board, we have vast quantities of MAX 4204 buffers. These are 780 megahertz line drivers, 2 per package, that have a built-in termination resistor for driving a 50 ohm coax. So yeah, there's 32 of them for the 64 analog channels. There's also 4 more of those quad DACs. These seem to be providing the other side of the differential pair. So one of the say the positive side of the differential pair going to the ADC is driven by the line driver. The negative side is driven by the output from these DACs, so that you can set the offset of each channel, or actually each group of 2 channels, because we have 32 channels here with 64 analog channels. So what they seem to be doing is each channel of the DAC controls the offset for 2 of the analog channels. And I think that makes sense because the image sensor on this reads out 2 pixels vertically on top of each other, so the offsets would be the same for those 2, so you can use the same channels on the DAC. Okay, just mark which way this goes in so we remember. And, there's the image sensor. That's really cool. A few more, not too much else on this board, a whole bunch of footprints for parts that are not fitted, and just a bunch of capacitors. Let's see, is the image sensor say anything on it? No. Completely unlabeled, but I believe these are made by, it was initially made by Phil Factory, which was then bought by Cypress Semiconductor, and then that division was later bought by ON Semiconductor, who now owns it. I'm wondering what this thing written on here is. I wonder if that's some sort of calibration value or something, or a serial number. When I did the Phantom V4 teardown, the image sensor was 1024 by 1024, but they were only using 1/4 of the area, a 512 by 512 pixel area, and I had an inkling that that sensor was the same as is used on this camera, the Phantom V5. So if we put the image of the 2 sensors side by side, yes, they do seem to be identical, so my inkling was right. It makes sense that you would use the same image sensor on both cameras, because the amount of NRE or engineering work required to design a custom image sensor like this is astronomical. I can imagine it would cost many hundreds of thousands of dollars to have a custom chip like this designed. So it makes sense to spread that out over as many cameras as possible, or design the fewest number of custom chips possible. The machining on this camera is really quite complex. They had to come in from numerous different angles, pretty much from all sides to machine this. It really is quite complicated. Like this, so this image sensor mount is another machined piece out of, yeah, it's aluminum. I thought it was plastic for a second, but no, that's aluminum as well. Here I've drawn out a basic block diagram of the camera. We have the image sensor outputting the 64 analog channels. Those channels go into 64 analog buffers. The outputs of these buffers are combined with the outputs of a DAC to form differential channels. There's 32 DAC channels. Each one DAC channel drives the negative output of 2 of the differential channels. The ADCs have adjustable VREF values as well, with another DAC, again outputting 32 channels, and each single channel driving the VREF of two ADCs. The image sensor and the buffers and this DAC are on the image sensor board, or the 2 boards that are in the front of the camera. These then go over the cables to the individual memory cards. There's 4 memory cards, or 4 acquisition cards. Each of them have 2 of the RAM slots with 16 ADCs. I've drawn out 8 of the channels which connect up to 1 of the sticks of RAM. And each channel goes into an ADC and then into a FIFO that buffers the data for as it goes into the RAM, and it also provides and it also allows for the change of the clock rate. The image sensor runs at a 20 megahertz pixel clock, so everything up until this line runs at 20 megahertz, and then everything right of this runs at 40 megahertz. That allows time for the data to be written into RAM faster than it comes in, so there's time for it to be read out into the rest of the system for display. On the acquisition card, or as it's labeled, the memory board, the RAM has its own little bus that goes between the FIFOs and these tri-statable bidirectional bus buffers and registers. And these allow data from the memory to be read out onto the rest of the system. The 64-bit memory bus connects up to 4 of the 16-bit buffers for a 64-bit bus, and the outputs of those are then combined into a single 16-bit bus. So when a read is done from memory, it would read from the memory into all the registers, and then you could individually read out each 16 bits on a different clock cycle. And there's the other stick of RAM on the memory board connects to another 16-bit bus. This whole thing you see here is duplicated on the same card, and there's 2 16-bit buses that end up leaving the card onto the another bus, and this bus runs between all of the cards. So there's 32 bits wide, and this goes to the other 4 cards that are farther up. So the data from any of the sticks of RAM can be read out onto these buses. One thing I don't notice anywhere in the system are configuration memories for all of these FPGAs. That means that the configuration information bitstream has to be stored in this flash on the processor board. So that means the CPU over here has to configure all these FPGAs over something like SPI. And this camera did take a long time to boot, something like 10 or 15 seconds, so that makes sense. It has a lot of FPGAs to configure. I was curious as to how they identify which card is which, because all of these are basically bused together. I was thinking they may have done some sort of arrangement with sort of an offset bus that like moves over each time it goes through these connectors, but it looks like they're just doing it with some little jumper links. There's 2 solderable links here connected to this FPGA, and each card is different. This one has the top soldered, this one has both, this one has the bottom one, and as we'd expect, this one has none. So that's how they're identifying which cards they are. So it looks like it does matter which order they go in, because if you put them in the wrong order, you will get the wrong data read out during image readout. That might have explained why the bottom half of the image was reversed, because these cards were in a different order than they had been numbered. I guess it's just someone was careless when putting this back together. Okay, let's see what this does. Booting up. I have a little temporary heatsink on that regulator just in case it gets hot. Yeah, this does have a pretty decent boot up time, and yep, we're still getting the same problems. I was just playing around with the order of the cards, and that does seem to change the position the image is in, but I was just bumping it. It does seem to be some sort of an intermittent connection, because that was, when I bump it, it does change. But that will be for the repair video I'll do on this. So that was a really interesting teardown of in its day, cutting edge and surely very expensive high-speed camera. I'm sure this thing sold for the high 5 figures back when it was released in 2001. Anyway, hope you found this video interesting. Stay tuned for the repair video or repair attempt video. Thanks for watching.